So, I welcome you all in today's talk. And the intuition is that we would like to get some philosophical touch to understand in a philosophical way the meaning of perturbation. And I would like to start with an example. I have imagined a couple of small stories that I would like to share with you. And these stories will guide us to whisper, to understand the meaning of perturbation in physics. Now, to start with, if I imagine that there is a lake, at the dawn, there is a lake, and this lake is silent. There's no disturbance acting in the lake. And this lake is acting as a mirror to the sky. You can see the sky at the dawn. You can see the reflections of the sky in the lake. Now assume a pebble in your hand. A pebble in your hand, and you drop this pebble in this lake. Now what it does, it creates waves, it creates vibrations. And there is symmetry in those vibrations. So what you are doing is you are disturbing the calmness of this lake. And if I think in terms of the ideal problems that we have solved in quantum mechanics, the problem of a particle in a one-dimensional box, they are the lake that I described you. But when you disturb this lake, that too over a period of time, that disturbance causes the change. Even though that change is extremely small, for a short note of time, this reflects perturbation, time-dependent perturbation. So, you are able to sense the symmetry that evolves in that lake by virtue of that small disturbance that you are inserting in the lake. Now see, there is not anything like violence. You are not allowed to throw the stone in the lake. When you throw the stone in the lake, it becomes violent. And this violence leads to scattering. That's your fourth chapter. We are not violent here. We're very subtle. Let me take another example. Let us assume that I'm in a room and I carry a tuning fork. You have seen a tuning fork in the laboratory. We have a tuning fork when you perform that experiment of sonometer. And in this room, there is a violin. You understand violin? It has strings, it has wires. Now, if I disturb the tuning fork here, it will vibrate. you may listen the vibrations from the violin. You're not touching the violin. The violin is in the room, but there is a possibility that the vibrations that you're producing in the tuning fork, their frequencies may match the natural frequency of the wire of your violin. If the two frequencies match, your violin will vibrate. Are you getting my point? Without making any physical contact to the violin, the resonance makes it possible. The perturbation makes it possible. Because the disturbance that you have generated, it has a frequency. If it has a frequency, it has a dependence on time. This disturbance has a changing nature in the background of time. That's what is called time dependent. And what is time independent? What's time independent? You are disturbing your system, but the disturbance that you are using is a constant. It does not depend on time. It remains same. It's not changing. So when your disturbance changes, you have a dependence of time. So in the background of your calculation, you have time. You have a mathematical equation. What you do now, you incorporate time in your equation. So when you incorporate time in your equation, you talk about the time-dependent perturbation. Now see, everything is not possible. I use a tuning fork in my room. Only certain vibrations are allowed that will match with the frequency of the violin. So in quantum mechanics, you have allowed transitions and you have forbidden transitions. It is not all the frequencies of the tuning fork that will match with the frequency of the violin. Only some selected. And giving birth to what's called as selection rule in quantum mechanics. You have allowed transitions and you have forbidden transitions. Now I want to quote down another example to understand the same thing that I'm trying to explain. Now let me assume that I'm in a ground and this ground is filled with fog. It's filled with haze. Okay? So when it's filled with haze, I can't see. I don't know my destination. I don't know where am I going. Imagine in that haze, there is a lantern. And a lantern lights somewhere in a haze. It just lights and closes. What will I do? I will follow the direction of that light spot that I saw. I saw it for a very short span of time. What was my identity before that shot of light? I was everywhere. I had no destination. But a small flick, a small click of light, it changed my course. I moved towards that light. So this is how quantum works. Sometimes new paths come in action. These paths don't exist. But these paths have an origination by virtue of that perturbation. Lighting up the lamp. I am in a haze. I am in a fog. I see a short flash of light. And I move in that direction. This is how time-dependent perturbation works. Getting my point? So what we have, we want to understand this. We want to have some more deep understanding. I think these examples, they certainly might have given you some idea that what actually we are doing in mathematical framework, what our intuition is basically. You have a disturbance, but that's a beautiful disturbance. That does not disturb the lake in a violent fashion. Your disturbance causes symmetrical wavelets in a lake of water. Your disturbance causes a person to know its destination when it is trapped in a fog. Your disturbance vibrates a violin which you have not even touched before. This disturbance is time-dependent disturbance. So we call this as time-dependent perturbation. Alright? So again, I will go with the same thing because I want you to have a catch on it so you understand what perturbation is. It is a kind of disturbance that you disturb your system. That system is in a sleep. And you feel you know everything about this lake. It's a sleeping lake. We know it. We solve the Schrödinger's equation. Okay? So, you gently disturb the system. We assume that we understand system already without the disturbances. We assume we understand. Then we tweak it slightly and see how it responds. So, what is the nature here? Talking about the classical objects, talking about moon, talking about football, talking about planets. Certain, you're certain. You are completely certain in the classical domain. You have an object, you know the initial conditions, you can exactly predict. You are certain where the duster will fall, how much time this duster will take to reach the target. So in classical physics, you deal with certainties. You're certain about the outcomes. But here, you are dealing with probabilities. Your results are probabilistic. Now think about the person in a haze. How will I define this person moving in a fog? I'll say it has all probabilities. It can choose any path. Maybe it's everywhere in the system. So this is how quantum mechanics works. It does not work in the framework of certainties, it works in the framework of probabilities. You talk about the probability that there will be a transition of an electron from ground state to excited state. You don't say that it will. You simply say it has a probability to make this transition. And it has a probability not to make this transition. Both statements are true. Right? So your quantum systems are defined by possibilities, probabilities. They live in a world of probabilities rather than that of certainties I was talking about. A state describes what a system is doing. Okay? We don't have the physicality of that state, the wave function, right? Or more precisely, what it might be doing when I will measure. These are the two faces of the same coin. Things are happening in presence when you try to measure, and things are happening when you don't measure. These are two different worlds in quantum realm. Now again, see, because we are discussing the time-dependent perturbation, the point is why time matters. Why time matters? Because you are inculcating the change of the disturbance. Your disturbance is changing, and that change can be measured in time. Right? So time adds the flow and the evolution. You have evolution operators in quantum mechanics. You evolve your operators in the framework of time. When changes happen over time, the system evolves. Sometimes smoothly, sometimes dramatically. So dramatically here is directly telling us about the scattering, right? So when I say dramatic change, that's scattering. When I say that you have a smoothie kind of disturbance, then certainly I'm talking about the perturbation. And certainly perturbation seems to be more fundamental. It seems to be more beautiful than that of scattering. So time lets us explore. Okay, you started somewhere, you ended somewhere. Not just what is, but how things become. Okay. So we have two frameworks, time dependent. Now how can I differentiate the two theories? In case of time independent, the disturbance that you're adding to a system is constant. It doesn't change. I apply the magnetic field. I'm applying a constant magnetic field. I apply the electric field. I apply the force. Anything that causes disturbance to my system has to be constant. So if it's constant, then it does not depend on time. Get me to the point? And when I add the change of my disturbance, even if that disturbance is very, very short, a small pulse, then certainly your system is going to evolve in the framework of time-dependent perturbation theory. So a pulse, a wave, or a flicker, this distinction changes everything about how the systems behave. It changes the course completely. What you understand in the framework of time independent changes totally when you discuss the same problem in the framework of time dependent disturbances. Now, this is how we approach the complex problems, because we cannot exactly solve the complex problems. Mathematically, we are weak in solving a three-body problem. Even for two-body problem, you use a lot of paper. And if you have to solve a three-body problem analytically, it will take 3-4 copies. For that, you need simulations, you need approximations to get some information about the system. So, we know the full picture of the lake which was not disturbed. We know the full picture of the haze in which the person was standing. We know the full picture of the tuning fork that was not doing anything. We know that mathematically. But what we are adding here is the disturbance, a short disturbance. So this approach helps us to navigate complexity by staying grounded in the simplicity. Now what is the simplicity here? Come on. The sleeping lake, the lake in the dawn of the day, in which you can see the reflections of the sky. That is the simplicity. That is your unperturbed Hamiltonian. Getting my point? Right. Again, time-dependent perturbation theory asks us, how does a quantum system respond to a changing external influence? And this could be a flash of light, as I said. I gave that an example. Can be that flash of light, a varying field, or any temporary disturbance that you can think of. It means the change is not violent or overwhelming. We are just nudging. We're just nudging the system, not smashing it apart. This keeps the original identity of the system mostly intact. A sleeping lake with the waves that you produce when you disturb it by a small pebble. You predict the possibilities. You're not certain about the results. You don't predict the certainties. You predict the possibilities. If nature would have been like certainties, people will not die. We will have no end. It will be completely possible to give you an infinite life. But the Creator is playing with possibilities, it's playing with probabilities. That's why we die, the things go off. So quantum mechanics never says what will happen, only what might happen. Suppose a person is there, has a disease. What science can tell about this disease? Suppose it's a very dangerous disease. It will give you the probabilities, but it will not be in a position to completely cure the person, because his machines, his actions, they are all based on quantum mechanics. And quantum mechanics works on probabilities. There is a probability that this man will die. There is a 30% probability he will die. There is a 70% probability that the man will live. That's why in real world we have probabilities. So quantum mechanics is more fundamental than any of the sciences that we have around. It's more fundamental than biological sciences. It's more fundamental than chemical science. It's more fundamental than any science that's there in this planet. The energy levels, they dance when you exert that disturbance. Now see, imagine energy levels like a different floor. This is a floor 1, there's a floor 2. Okay? Now, to make a transition from floor 1 to floor 2, if you say Newton, what does that mean? I have a ball in this floor, this ball has to go to the floor 2. What does Newton mean? Come on, give the force to the ball, this much of force, the ball will go into the floor 2. That's Newton. But that's not if you have a quantum system. You have a quantum floor 1, you have a quantum floor 2. You have to give the right energy, you have to give the right disturbance at the right time. Only then you will have the probability that this ball will go into the floor number 2. For Newton, it's not possible. It's not a big deal. Okay? But for quantum framework, you need everything accurately, because there are a lot of things that are forbidden. Could you imagine for a ball in floor 1 that this ball will be forbidden if all the forces are available? Even if a giant is on this door, you will throw the giant, you will take the ball in your hand, you will face everything, and you will go to the floor number 2. But that's not the case here. What is important here is the jumps. But these jumps are dependent on timing. Appropriate strength. From Newton's point of view, you can throw your ball to the 10th floor, depending on the amount of energy that you are using on that ball. But here, you need the timing, you need the strength, appropriate, and the compatibility. why that violin was buzzing. Why? Why was that violin buzzing? Come on, can you answer that question? When I used the tuning fork. Because there was a match. You may call it an emotional match was there. And that match led the buzzing of that violin. If it would have mismatched with the violin, maybe the violin would not have responded. So these are the real world analogies. You can see them. A child on a swing being pushed at just the right rhythm. A violin string vibrating when another nearby note is played. A whisper that grows louder until it changes your mind. These are the examples. They talk about the timing. They talk about the harmony. And your system is transforming. This is what perturbation is. That's why when you deal with solving the problems, you see those symmetrical equations. You have sine thetas, you have cosine thetas, you have symmetries. You're always looking for these symmetries. Now, your disturbance can be sudden. If it is sudden, it is not perturbation. And it can be slow. When it is slow, it is perturbation. But when it is sudden, it's certainly scattering. It's certainly something that's happening violently in the system. These extra forces. What can be these extra forces? Light from a laser, a pulse. It can act as a perturbation. But it has to be a pulse. In case of non-degenerate perturbation theory, it was not a pulse. Keep that in mind. It was a constant disturbance. Its magnitude was same. That's why you have a time-independent perturbation theory. Getting my point? But here you have a pulse, a magnetic field, electric field, a vibration. They all influence the quantum systems. And these are all disturbances that are dependent on time. As I was saying, flow 1, flow 2. Okay? A quantum state can make a transition, like changing moods or identities. Now see, sometimes suppose I'm sitting here, I'm talking to you. My mood can change. Maybe I'm happy right now, I'll be sad. Maybe I'm less happy, I'll be more happy. What's happening in me? There are transitions. These are quantum mechanical transitions that are happening in my body. And they are making that sense to me. But it's not like that every time I laugh. It's not like that every time I cry. It's not like that every time I'm serious. But whatever am I am making transitions. And why I am making transitions? Because I'm influenced by the environment around me. The atoms of which I am made of, they are making transitions. Right now, I'm in a mood to give a class in this classroom. I will find a transition. I will leave the room. Getting my point? So these transitions are equally valid in our day-to-day lives. Because they are all probable. I will stand up this boy in this room, and we will all go out of this room. Say, for example, what this boy will do. Do you know? But he has many possibilities. He can feel, I will sit for a while. He can have something in his mind. He will open the door. Or he will see outside. Why he is doing that? Because the transitions are acting in his brain. There are atomic transitions that are happening in his brain. And that's leading us to have all these actions. Let's not go so deep. So this is the resonance that I was talking about. Resonance between the tuning fork and and the violin that you have. So resonance is like perfect alignment in timing. See, time makes beauty here. When an influence matches the system's natural tendencies, what's happening? It responds strongly. It responds strongly and efficiently. Resonance leads to the rapid and likely transitions. The violin was not responding, it was dead. I'm in the room tuning fork, hitting it. A small vibration. The vibration matches with the vibration of the violin. It responds. There is a resonance. You understand the resonance? The frequency matching. When the frequency of the two things match, what happens? The amplitude is maximum. That's what resonance is. And that's what quantum probabilities are. These are the resonances in the background of time. So resonance leads to the rapid and likely transitions. As I said, all transitions are not possible, which is not the case of classical physics. In classical physics, all energies are possible. You cannot think, if I threw a ball, can you imagine that at any point this ball will have no energy? It has continuum of energies, right? But in quantum domain, what we have? We have discrete energies. We have possible transitions. We have forbidden transitions. Atoms absorbing light and becoming excited. Medical imaging, you can see my skin by perturbing my skin by an external force. It can be a magnetic field, like we have in MRI, right? It can be a CT scan where you use a radiation, make them interact. So, what we have, where quantum jumps, power, lifetime dependent effects are everywhere. You will see this. This is happening everywhere in the universe that we are studying. It's the core of everything that's happening around us. That's what's called as life. It has strong implications on the modern physics. In all frameworks, in all domains. It helps us understand how atoms emit light, how quantum computers process information, how particles behave in early universe. It's really foundational for the technology and the theory of that. So, this is the summary of the key ideas. I think I have taken care of all of these points. You can go to Feynman book to have more philosophical understanding on it. And these are some of the important books that you can use if you are very much interested in understanding the philosophy of the subject. And still, you see, there are questions. There are open questions. Don't you believe that if man would have answered to everything, man would have declared himself as God? And it's the quantum mechanics that's giving us all of these probabilities and making people believe that there is someone who has created us. Now, it doesn't matter whether we are Muslims or Hindus or Christians. No, the point is there is a complete understanding that things are not in our hands. We are being governed. We are governed, whatever we are. So can we fully predict how a system will respond? What is the nature of influence itself? Is time a background stage? The time I was talking about. I choose this time on my copy. Does it actually exist there? I don't know. I'm not sure about that. But the time is something fundamental. But I understand the results. When I get the results, they dictate me, they tell me that, come on, there must be the time. Because the results that I'm obtaining, they are matching with the experiments. So with this, I think this is the end of this. So I hope I have tried to make an impression. I have tried to make you feel, make you realize what we are actually discussing. So with this, I would like to thank you all. So, bye. Okay, a very welcome to all of you. And today we have to go on with time-dependent perturbation theory. We will actually subject ourselves to the mathematical treatment of this time-dependent perturbation theory. But before I start the mathematical argument, I remember they happened to have a man. He was a scientist, and he was performing an experiment in his laboratory. And this man was repeatedly working on discharge tubes. And the intention was that you could develop the rays within those tubes where he had to attain some state of vacuum. And this man repeatedly performed his experiment, and every moment he performed the experiment on these vacuum tubes, he failed to obtain a conclusive result. And one day he was fed up. Thought, come on, it's not happening. I'm not able to get anything out of it. So he takes a holiday. He doesn't attend laboratory for quite a long time. And then one fine morning he returns back to his laboratory. And when he returns back to his laboratory, he finds a piece of paper in his laboratory. And when he looks at that piece of paper, he finds a glow on it. And a question arises in his mind that he did not attend this laboratory for quite a long time. Why there is a glow on this piece of paper? And the man had discovered X-rays. The name of this fellow was Röntgen. In Russia he is called Rankin. And you can understand the importance of X-rays in the modern time. It's a blueprint that gives the design of your bonal skeleton. So this is how science goes. Science does not mean that you will do it and it will happen. Most of the science has come via the failures. So let's proceed. We have already gone through the theoretical understanding of time-dependent perturbation theory. Now we will go with the pure mathematical approach for this theory. So what we have a perturbed Hamiltonian, and the perturbation is time-dependent. I have exclusively discussed the time dependence of perturbation in my previous lecture, right? So today we will go with the model, and the target is perturbation, and it is time dependent perturbation. So obviously you have a perturbed Hamiltonian, right? And if I say I have a perturbed Hamiltonian, that is H, that must be something H naught plus lambda HP. Right? As I told you yesterday, that to understand the behavior of your system, what you do is you send a pulse of disturbance. The magnitude of that disturbance is extremely small, but that disturbance gives us a lot of information about the system. So, the basic equation that we have in quantum mechanics that we use to solve for our systems is Schrödinger's equation. Now, I would like to write down the Schrödinger's equation. Okay, so what's Schrödinger's equation? It's I h bar dou by dou t. If I choose, say, psi n of t, and I will put this eigenstate in Dirac notation. This is your left-hand side of the Schrödinger's equation, and the right-hand side is simply your Hamiltonian operator acting on the eigenstate psi n, which is a function of time. Now this is my time-dependent Schrödinger's wave equation, and we understand that we can write down the current eigenstate in terms of the superposition of the eigenstates of the known eigenvector. So for that, I would like to write down this eigenstate psi n of t. What will be that? Yeah, this psi n of t, it will be a superposition, say sigma. Okay, I will use, say, a it's a coefficient dependent on time. Let me put some subscript here, a n of t. I will use an exponential e to the power of minus I e n of t by h cross, and an eigenstate, say phi n of t. Now what am I doing is writing down this eigenstate in terms of two time dependent parameters. This coefficient is dependent on time, and this exponential is also dependent on time, but I am incorporating a eigenstate which is independent of time. That is phi n. I should not write t here. So let me write, say, phi n of r. This eigenstate does not depend on time. Okay? Now, what should I do? Because the demand of the Schrödinger's equation is I want the eigenstate, the time derivative of eigenstate. So for that, I would like to differentiate this, isn't it? Because if I want to use this format of eigenstate in the Schrödinger's equation, I need the derivative of this eigenstate. So what will I do? I will differentiate this equation with respect to time. So if I do that, what I'll get dou by dou t of psi n of t. Fine? Okay? So here you can see this part will not take role in differentiation because it's not dependent on time. So you will have the two parts. One is this coefficient part. It's dependent on time. And another is this exponential part. It's also dependent on time. So I'll be using my uv in this case. What I'll have sigma. Okay? A dot n of t. Okay? The exponential will remain as it's e to the power of minus iota e n of t by h cross. Okay? It will have its own time independent eigenstate, phi n of r. Right? This will be your first term. Now the second term will be what? Plus sigma. Now an of t will be as is. Now you have to differentiate this exponential, and you can see the internal derivative is minus I by h cross en. Am I right? This will be the internal derivative of the exponential, and your exponential will remain same, e to the power of minus iota en of t by h cross. And then you will have phi n of r. It's ket. Right? Okay. Now, what am I supposed to do? Is I'm supposed to use this eigenstate in my Schrodinger's equation, and I would like to replace the time-dependent derivative of the eigenstate psi of t in the left-hand side of Schrodinger's equation. Right? So I can do that. Now you see, what is in the left-hand side? You have IH cross. Then you have the time derivative of eigenstate. So what will remain inside? Yeah? Inside you are left with sigma a dot n of t, and then you have e to the power of minus iota en of t by h cross, and this is got its eigenstate which is independent of time, that is phi n of r. It's ket. Okay, this is it. This is the term 1. The term 2 is what? It is minus I by h cross en. Then you have, okay, you have a sigma, and then an of t, then you have e to the power of minus I en of t by h bar. Then you have phi n of r. It's ket. Right? This is our left hand side of the equation. And what about the right hand side of the equation? The right hand side of the equation is h. But h is what? H is h naught plus, I will not use lambda right now, I will use it later on. So I will keep it as h naught plus hp. But this thing is multiplied by the eigenstate. What is that? That is sigma a n of t, then e to the power of minus iota en of t by h cross phi n of r. Am I right? Fine? Very right. Okay. So you will have two independent terms in the right hand side. The one term will be sigma a n of t and e to the power of minus iota en of t by h cross. Then you will have your h naught phi n of r. This will be the first term. Okay? What will be the next term? It will be in terms of HP. So I will write that, but before moving on, you see this IH cross will multiply to this, it will remain as is. But when it will multiply with this, what you will get? Iota scalar will give you minus 1. It has its own minus, so it will become plus. So what should I do? I should put here a plus sign, because h cross will be gone. And I will remove the bracket here, because this IH cross is the part of this part of the equation. And for this, you have plus En. Is this fair? Clear?
Yes.
Can I move on? Okay. Now you will have another term. What will be that? That will be sigma a n of t, yeah, e to the power of minus iota e n of t by h cross. Then you will have hp, and then you have phi n of r. Are you understanding what am I doing? Okay?
Plus term.
Yeah, this is plus. Right? Come on, come on. Now look at this part. Look at this part of the equation. You have h naught phi n of r. What will it give us? En. What will it give us En? It will give us En. So this term and this term are same. This term and this term, they are same. Here you have to use the eigenvalue equation. That will lead us to the same energy eigenvector, because your Hamiltonian is a Hermitian operator here. Okay? So what you are going to get, this term will cancel with this term. Right? So what we are left with? We are left with this term and the term on the last. So what is the first term? Come on, tell me. So it is I h cross summation
an
dot. You keep in mind that this an dot is basically d by dt of an. So the dot is representing here the time derivative of your coefficient an. So what will be left here with? Okay, this is, yeah, come on, e to the power of minus I e n d by h cross
phi n of r.
phi n of r. Now this thing is equal to this thing. Is this clear?
Yes.
Clear?
Yes.
Now this thing is equal to this thing. Now what should I do? I will use the same basis and I will take a bra phi m of r. And what I will do? I will multiply this equation from left using phi m of r. Clear? Clear? So I can do that. When I do that, so what am I doing? I use an eigenvector belonging to the same basis with different indices, phi m, and I multiply this with the equation that is in front of you. Okay? So what will I get? Should I arrange it here? No, I will write it again. Come on, tell me the term now. Come on. You have sigma, yeah, you have an dot of t, then you have something e to the power of minus iota en t by h cross, and then you have a ket of phi m of r and the bra of phi n of r. Is this clear? And what about the next term? That is sigma an of t. Then you have e to the power of minus iota en of t. Okay, that's fine. Then you will have the matrix element phi m of r, the perturbation that you have introduced, and phi n of r. Is this clear?
Yes. H cross. E.
Yeah. Where is h cross? Here. Divide by h cross. Okay, what about this term? This term will exist for m is equal to n, because this phi m of r and phi n of r is a canonical delta. It is mn, and it will exist for m equal to n. It will give you 1. m equal to n. Okay? What? M equal to n. So with that, when I use this orthogonality condition in my equation, what I will do is I will trick my equation because I want to make my equation comfortable. So to do that, since I am using m equal to n, in the left hand side for n I will use m.
Yes.
And in the right hand side I have n. Getting my point? Okay, so what I will write now? Come on, come on. So what will I write now? I will write sigma a n dot of t e to the power of minus iota em of t by h cross. Getting? This is equal to, yeah? This is equal to sigma. What about the IH cross? That is here, I think, huh? IH cross. Or it is in the left hand side. It is in the left hand side. Sorry, it has to be in the left hand side. Okay, so this is IH cross is here. Okay? So this is equal to, yeah, come on, tell me, this is AN of t, and then you have e to the power of minus iota En of t by h cross. And then you have the matrix element. Phi m of r, and then the perturbation phi n of r. Is this clear up to this point?
Yes, sir. Yes.
Are you following me?
Yes.
Okay, are you getting it? Okay. Now what can I do? I would like to bring this down, okay? What else? I would like to keep it in the left hand side sigma an dot of t. Okay? In the right hand side what I will get? 1 by IH cross. This is the first thing. Now the next thing will be what? Sigma, yeah? A n of t. Very fine. Then I will write my matrix element. H m n. I'm writing it in the short form, okay? And e to the power of minus e to the power of iota en minus em times t by h bar. You can do it and you will see it, okay? Because when this will come down, then you raise it up, then you will have e to the power of iota en minus em times t by h cross. Clear up to this point? Okay? Now, let's write down this equation again. Now this is en minus em by h cross. What is it? Yeah. En minus em by h cross. What is it? Can you tell me? The only question I'm asking you. Give me the answer to this question. Come on. So what we have sigma an dot of t, okay, is equal to 1 by IH cross. Then you have sigma an of t. Then you have matrix element. You remember that this perturbation part has lambda with it. Okay, I would like to introduce that lambda here. So this is lambda, and then h mn, it's that matrix, okay? And then e to the power of I. Come on, you're not telling me. It's a Bohr's postulate. It's a Bohr's postulate. The conventional Bohr's postulate. What it tells us. Don't you remember that postulate? It tells us that the difference in the energy levels is what? You don't remember the Bohr's postulate? E I minus EF is h nil. Now you see, this is ei minus ef. Now h, I want to make it h cross. What should I do? I should multiply and divide by 2 pi. So this is h by 2 pi, and then you have 2 pi nil. Now this h by 2 pi is what? This is h cross. So ei minus ef divided by h cross is, what is this? 2 pi nil. What is it? 2 pi nil. Come on. It's omega. It's angular frequency. This is omega. So here it is e to the power of I omega mn t. Right? Okay? So for mn, this is I and f here, okay? You can choose it as m minus n. So this omega mn is what? It's the angular frequency. It's the angular frequency. Clear? You got it? So now what I have an of t, an dot of t. I can write it as an0 of t plus an1 but with lambda of t plus lambda square an2 of t. It has to be dot, it has to be dot, it has to be dot, okay? I can expand it like this. Okay, I can expand this part also, which is an of t. What will be an? What will be the first term of an of t? Come on. What will be the first term of an of t? It will be lambda an0 of t, because you have lambda multiplied. So that what will be the next term? It will be lambda square an1 of t. Are you getting? Plus lambda cube an square of t plus so on and so forth. Is this clear? So you will have zero order calculation of perturbation, because you will compare the coefficients. Okay? What will be the zero order calculation? So for zero order, this term, which has a power 0, it has a dot on it, it will be equal to what? It will be equal to what? It will be equal to 0. Why? Because there is not any term in the right hand side without lambda. Right? So the first term will be what? The first term, that's called the zero calculations of perturbation. That is an dot of t will be equal to 0. What does that mean? That means an of t is constant. Am I right? Is it constant? Why? Because it is an dot. It is d by dt. And integration of 0 will give you a constant. Clear? Okay. Now, what about the second calculation? For second, you will have an, yeah? An dot 1. And what will come in the right hand side? an0. Are you getting my point? And so on. So I can generalize this solution. I can write an, say, k plus 1 dot, okay, is equal to sigma. Now let me take off this sigma for the time being. Okay, what you are left here with? An of t.
K.
It will be only k. It's k plus 1. Right? And then h m n. Right? And then e to the power of e to the power of iota, omega, m, and t. So you can calculate all the orders of the results of the perturbation. What is in the left hand side? It's a dot. It's a derivative. It's a... I forgot something. What was that? That was IH bar. IH bar is in the denominator of the right hand side. Okay? So now, finally I am writing the amplitude. Now what is my amplitude? It is A. Yeah, it is A n of t is equal to 1 by I h cross integral 0 to infinity. You understand where from the integral has come? See, I have taken off the dot. Okay? So then you have here A n of t. But this one is k plus 1 and this one is k. Right? And the matrix element m h p n, right? E to the power of I omega m n t. So here we will stop. Okay? So this is the basic formalism that we have reached out, and what we have is the amplitude. Is the amplitude. Okay? And from the amplitude you can calculate the probability density. All you have to do is to take the mode of scale of this amplitude. You will be calculating the probability density. And this probability density that you will be calculating, you will have the cases. You will have constant perturbation, constant time per perturbation, and you can have varying time perturbation. Okay? These cases we will discuss in our next lecture. So anybody having any questions? You got this?
Yes, sir.
So you can do it. So really, okay, thank you. Hi, hello. Basically, I have a point to make. I have a point to share. You can see candle. Assuming this to be a candle. Now, you can think about a candle. And when you will think about a candle, you will certainly come across, you will find infinite number of questions when you will actually look at this candle in a deep night. Assuming there is a thunderstorm going on, there's no electrical light in the room you're sitting in, and you just stand up and lit a candle. And when you look at the candle, you have many things in your mind. You can think that why the flame of this candle is rising up. Why this flame is not falling down. can think of why there is a need of oxygen for this flame to actually come in action. You can feel, you can think about the energy that this flame is giving to its environment. To be precise, you will have a long range of questions, and if this thing lives in your mind, it certainly makes you a point. And when you will go into a dark room, when you will go into the bedroom, you close this light, you will come up across a range of questions. Maybe this event will cause a curiosity in you, and you may feel attracted to something that you keenly looked at. You came up with questions, and maybe you go inside the room, sit in front of a table, lit up a table lamp, and open the books to understand why things are happening the way I observe them happening, and why they are not happening the other way. So the point I'm trying to make here is we can reason everything that's happening around us. And to reason, you certainly have to be rational, and you have to explore the mind, the intelligence that's given to us. Now, it can be a starting ignition for you, and this flame of the candle can take you to any extent where you can satisfy yourself with the probable answers surrounding the questions that you raise in your lifetime. It doesn't mean that you will not be able to suffice a luxury out of it. But being humans means there is something extraordinary. That's why we are humans as a race on this planet. And we have a job to do. We have to use the intelligence that's given to us to explore the science, to explore the universe, to explore the microscopic universe. Even though we don't come up with the exact answers to the questions that come across, but the process of engaging yourself to understand is a great job. And it's something that lets us peace. It's something that gives us pleasure. And we as humans should focus more on the scientific realities. And certainly growing a society in the framework of science seems to be better than that of a society with no touch of scientific thoughts, scientific arguments, scientific laws. So this was a short piece of thing I want to share with you. I hope you like it. Bye. Okay, I welcome you all, and I would like to continue our discussion on time-dependent perturbation theory. And in our previous class, what we have done, we have obtained an expression for the amplitude of the perturbed system. Now, before I go on with this crazy mathematics, let me give you another glimpse of. I want to talk about a person who belongs to this country, a person whose name was. I would reveal his name in a couple of minutes. And this man, it's believed, maybe it has come from the stories, that this man had an imaginative thought experiment. And this thought experiment was, it was based on a candle that has a flame. In fact, there is another inspirational story I can tell you about this candle carrying a flame. But before that, let me focus on this one. And probably this was the time of wars. It was in 1940s time. The war in the world was it was on its peak, and people were involved in playing wars, killing each other, playing politics and all that. But this man was sitting in his room, and he was trying to understand something. And he was sitting in a room in Princeton. And this man had an origin from India. And his name was Subramaniam Chandrasekhar. He was a thin, flat man, but a very good thinker. And in fact, maybe this thought experiment has given him an idea. The thought experiment of a candle, having a flame. Now, if I have a candle, it has a flame, even a small whisper is capable of disturbing this flame. Not only disturbing the flame, it can shut the flame of your candle. And what this man believed that a small disturbance, because he was trying to understand the instabilities of the stars. The world was running with wars, but this man was thinking about the instability. And he was able to guess a very, very strong argument about instabilities. And what was the argument? The argument was that if a small whisper is capable of creating a big change in the candle, the flame of the candle, the small perturbation can decide whether a star will shine its light for millions of years, or this star will turn into a black hole. A small disturbance in the star, a small perturbation. See, we are discussing the quantum mechanical perturbation, but this man was again looking for that perturbation, that a small change in a star can make this star shine for millions of years, but at the same time, if there is a small deviation from the expected one, this star can turn into a black hole. And in his time, there was a popular physicist, Arthur Eddington. According to him, he completely rejected the idea of Subramaniam Chandrasekhar. He completely rejected it. Said, doesn't work. But when black holes were actually discovered, this man received Nobel Prize in physics. And he proved the people who thought that this man is giving a ridiculous idea. This idea is not going to work to decide the destiny of a star, whether it will live for millions of years onwards or it will turn into a black hole by a small perturbation. And for this, the man receives Nobel Prize. And the answer goes to the community that whatever the man was looking for, he has got it right. So this is how science works. This is how physics works. This is how we should move on in our lives so that we can make an impact. Even if you feel that you have not made any impact, maybe it will reflect at some point of time. But what is important here is your sincerity. With what sincerity you are working your problems. So this was it. Let's move on with our topic that we have been trying to understand. So what we have is we have this a and 1 of t equal to the integral of the matrix element containing the perturbation part in it. Right? Now, the first thing that we will discuss is if you have perturbation in constant time. So, we will be discussing constant perturbation. Constant perturbation. Now, when I say constant perturbation, this perturbation that you have introduced, it's constant in time, right? So if it is constant in time, you can get it out of the integral, right?
Yes, sir.
So what will be an 1 of t? This will be 1 by I h cross, and you will have a matrix M, H, P, N, and then you will be left with 0 to t e to the power of I omega m n t dash d t dash. Clear? Now what we have an exponential function inside the integral, and we have to integrate this, okay? So this part is out because this is constant. So from here we can move on. Okay? So I will have a and 1 of t. This is going to be m h p n divided by I h cross. Now you integrate this. The integral of the exponential is an exponential, but you have to divide the internal derivative of the exponent. So for that, what you will get here, you will get e to the power of I omega m n t dash divided by I omega m n. So the limit will run from 0 to t. Clear? Right?
Yes, sir.
Yes, yes. Come on. Okay. So, what we can do here is, we would like to give the limits, and this iota will multiply this with this iota, it will give us iota square, that this will make our an 1 of t equal to minus m hp n divided by this h cross and omega n. Omega m n. Is this clear?
Yes, sir.
Fine. Okay, now inside I would like to give the limits. So the first limit will be e to the power of I omega m n t minus e to the power of 0. Am I right? So this is your upper limit is t and the lower limit is 0. That should be the case. Now what we can do? Okay, we can use a limit, say e to the power of I theta minus 1. And if this theta tends to 0, this will give us 2i sine theta by 2. So I can use this formula in my equation, right?
Yes.
So because this is e to the power of 0, this is equal to 1. So for this, I'll be writing this. I can move on. So what you will have? You will have a1 of t is equal to minus the matrix m, h, p and n divided by h cross omega m n. Right? Then you will have in the brackets, you will have 2i sine square omega m n t by 2. Clear? Getting?
Yes.
Okay. So this is my amplitude. And you know, this amplitude, it's a complex thing, and we will always like to calculate the probability density. And probability density will be what? It will be more square of this a1 of t, right? So from here, I can calculate the probability density. Okay? So the probability density. Probability density. Come on. What will be that? That will be an1 of t whole square. Right? You will take the mod of square of this, and this will give us what? This will give us the probability density. So let's do that. So it will be the square of this, so this minus will go,
Yes.
because you're taking the square of this. You will have the square of the matrix element. What will be that? That will be m, h, p, n divided by h cross square omega m n square. And this has its own square. Are you getting it?
Yes, sir.
Then you have in the brackets 2. 2 will make it 4. I will write 4 outside. Okay?
Yes.
2 square. I have a square minus 1, but it's the mod of that. So that minus will also go. So what you'll be left with? You'll be left with sine square omega m n of t divided by 2. Okay? So this is your probability density. And if you will plot this probability of density, taking your y-axis, let me do it on the next page. Okay, this is clear up to this?
Yes.
Now, if we plot it, and on x-axis we take omega mn. On the y-axis we choose sine square omega mn t by 2. Now what you come up with? You come up with a pattern like this. The figure has not become that beautiful, but you can understand it. Can you tell me what is this on your board? Have you seen this pattern before? What is it? Yes? Yeah, come on, what is it? It's a result of single slit diffraction. You remember that experiment?
Yes, sir.
If you have a light, you allow it pass through a single slit, then you have multiple interference things happening and you have a central maxima Then you have a minima, maxima, minima, maxima. So you can see that you have your result is somehow looking like that of diffraction due to a single slit, and you can certainly correlate it. So this is our case when we assume that the time is constant. Okay. Now, so this is called constant time perturbation. This is constant time dependent perturbation. And now we would like to move on to harmonic perturbation. That means I will perturb my system with a harmonic function, right? So the next thing that we'll be discussing is what? Harmonic perturbation. Okay. So what I have to discuss harmonic time dependent perturbation. Right?
Yes.
So in this case, what I will do, when my perturbation will become harmonic, I mean when I will perturb my system with a harmonic function. And let me choose that harmonic function as 2 sine omega t dash. Because when I am introducing a perturbation,
Yes.
it has to be harmonic. Okay? And why I choose 2? 2 gives me the mathematical simplicity. That's why I'm using 2 here. Different books will use different things. And you can have a problem based on the harmonic perturbation. This time I chose sine omega t. You can have a different harmonic perturbation that can be introduced in your system. But if we understand this, we can move on. We can move on to solve the problems based on harmonic time-dependent perturbation. Right? So, I have to start with my equation. So, what's going to happen? So, your perturbation is acting between 0 and t. There is no perturbation before 0. There is no perturbation after t. The perturbation is only acting for this span of time. Okay? So it's acting for 0 to t. So what will be my an1 of t? It will be 1 by I h cross. Then you have an integral 0 to t. Then you have the matrix element m, h, p,
And
n.
yeah.
Then you have e to the power of I omega m n t dash, and you multiply it with by 2
Yes.
and sine omega
T dash.
t dash.
T.
Now you see, the perturbation that I'm introducing in my system, I choose its angular frequency as omega because its frequency will be different.
Yes.
Okay? And this is the omega mn is the intrinsic angular frequency of your system. And omega is the frequency that you're introducing in your system.
Yes.
Is this clear to you?
Yes.
Now what I have to do, I have to solve this. And solving this will give me what? It will give me the amplitude, right? And then once I get the amplitude, I will calculate the probability density. So move on. So what should I do now? I can rub this. Yeah.
It's a time
Now
constant.
again, look at the things. The matrix element that we have here, we treat it as a constant. Because the perturbation that we have introduced in the system, we have given its value. It's 2 sine omega t dash. So what's going to happen? You will have a1 of t, then you will have 1 by I h cross out. The matrix element will be out. What you'll be left with? You'll be left with 0 to t. This 2 that you have here, okay, this 2 will come out. I will write it outside. Okay?
Yes.
And what will be left inside?
E upon
Sine omega t dash e to the power of I omega m and t dash dt dash. Am I right? Getting?
Yes, sir.
Okay. Come on. Now I have sine theta. What is sine theta? E to the power of iota theta minus e to the power of minus iota theta divided by 2i.
Yes.
Right? So we have that formula. Sine theta can be written as e to the power of I theta minus e to the power of minus I theta divided by 2i. Clear?
Yes, sir.
Now I will use this formula in my integral. So what will I get? I will get a and 1 of t is 2 by I h cross. Then you have h m n. I will call it h m n. Okay. Then you will have integral 0 to t. Then you will have e to the power of I omega t minus e to the power of minus I omega t divided by twice I, and then this will be multiplied by e to the power of I omega m n t dash dt dash.
इसमें t dash ऐड कर सकते हैं.
Yeah, here we have t dash. They're all dashes because I have to use the limit, right? So what can happen now? You see this 2, we get the rid of this 2 here. You got the rid? This iota square will make it minus. So a and 1 of t will be
Minus 1.
h m n. Do you get what h m n is? H m n is nothing but the matrix element. It is m
HP and
h p and n. Right? So here you will have minus outside. That's it. Then you will have h cross. Clear? Now you can multiply these exponential functions, and what you will get out of that? You will multiply them. What you will get? You will get integral 0 to t. You get e to the power of I omega mn plus omega times t dash, then minus e to the power of iota omega mn minus omega t dash. This should be the case, and you will multiply this by dt dash. Right?
yes.
Getting? Come on. Okay. Now all I have to do is to integrate these exponential functions. Okay? So when you integrate these exponential functions, what you will get? Okay? Here I will get the rid of integration. I would like to get it off, and I will get the rid. The exponential will remain exponential, but it will be divided by the internal derivative.
Yes, sir.
That is iota omega mn plus omega. Is it correct?
Yes, sir.
And here you will have iota omega mn minus omega. You see, come on, it has limits. The limits are running from 0 to t. Are you getting? Okay? So what will be the next step from here? Okay? You can see this iota. Okay, that's fine. Now you will give the limits. When you will give the limits, what you will
dt
get?
dash नहीं है,
Yes?
dt dash नहीं है,
Here is dt dash.
नहीं है, क्योंकि हमने तो
उसमें नहीं है।
Okay, sorry. Yeah, we have integrated it. Yes, you're right. There is no dt dash. There has not to be any dt dash because we have integrated it. Now we would like to give the limits. Okay?
Yes, sir.
So when you give the limits, what you will get? You will get a and 1 of t is minus hmn by h cross, and here you will have a long thing, e to the power of I times omega mn plus omega times t. I'm giving the limits, okay? Divide by iota omega mn plus omega. But it will have minus e to the power of 0 term, right? And then you have minus e to the power of I omega mn minus omega times t divided by iota omega mn minus omega, and this will be minus e to the power of 0. Okay? I think I can leave it here now, because what you would like to do after this, you would like to calculate
plus e of 0,
here. No,
minus minus होगा ना,
no,
plus
the minus is outside. I'm keeping it outside. Okay? Then you can do it in the next step. Okay? Then you can go on, and this will remain minus 1 and minus 1, and you can boil down this equation. Right?
Yes.
And when you boil down this equation, then what you will calculate? You will calculate the probability density. What will be the probability density? That will be A1 of t. It's mod of scatter. Okay? Then this negative term will go out, and finally you will come up with an expression where you will use the limiting conditions. Okay? So the limiting conditions will give you the details about the result of this perturbation. I mean, if you directly resolve it, you will get a harmonic kind of nature of probability density. I think you can do it, you can proceed. Okay? So this was it. Anything else you want to tell me? Yes? So if I go back to the same thing, the same story about the candle. Again, I'm trying to tell you that it's your intuition, it's your interest, it's your focus that matters. Again, I would like to tell you that you can find infinite number of questions, and the example can be the same candle. The candle I started this lecture with, which I connected to the great Indian scientist, to the great scientist of this country, whom we call as Subramaniam Chandra Shekhar, who was given the Nobel Prize. Now look at this candle. If you have a candle in your dark room, what do you observe in the candle? The flame. But this flame it's upwards. The very first question that can arise in our mind is why this flame is upwards, why it's not in downward direction. Okay? And if there is a small whisper, there are changes in the flame. The flame that arises in your candle, if you are curious, you will certainly try to go back to your room. If you have some books, you will try to open the books. Maybe you will not get the answer, but if you raise the questions about the flame that's coming out of this candle, you will come up with infinite number of questions. And it is these questions that take you towards the table in your room where you have books, and you try to find the answers to those questions that arise in your mind. And this is how science progresses. And what I believe is that every society should be literate in science. If a society has a scientific mind, this society will certainly grow. It will cross the limits. Getting my point?
Yes.
Any queries?
Yes.
So with this, I would like to stop this discussion, and I hope you will proceed this lecture yourself, and you'll try to solve some of the problems. So, very welcome to all of you. I hope everybody is fine, and everybody knows that we have been in the framework of perturbation, and we have taken on the basic mathematical method to reach out some of the important results of time-dependent perturbation theory. And today's target is Fermi golden rule, and it's a matter of very short period of time. But at the same time, in order to make this lecture series compatible, make it interesting, I would like to give you another example of the importance of perturbation theory. And a statement is given by a scientist, and the statement is that a flap of a butterfly in Brazil, you know the place Brazil? Is it possible that a swap of a butterfly will create a tornado? You understand the tornado? Will create a tornado in Texas. This was the argument given by a meteorologist. His name was Edward Lorenz in 1960. He was a meteorologist. And 1960, as all of you know, it was probably the beginning of computer age. And this man was simulating the programs. This man was preparing models, the weather models, the weather map. For that, they had to simulate the weather map. And what he does, on one fine morning, he has a data. We have a data, say 2.3147, 2.41322. He wanted to make his calculations very fast, so he thought, let me round off the numbers. I mean, if you have a number, say for example, 6.433217. 217, these are the last values in your number. What is their contribution? Their contribution is very less. Numerically, you don't put those values. So what he did in his simulation, he thought, come on, let me, because the processors used to be weak in those times, so that the computer has not to do a lot of work. What he did, he rounded off the numbers of his data. And when he simulated the problem, the results he obtained, they were massive. The changes he obtained in the new models using those approximations, the course of his weather model changed completely. It showed a completely different result. So what does it mean? It means small changes can bring a massive change in your system. This is why perturbation makes its it being an important tool of mathematics, important tool of quantum physics. It's the small change that leads the formation or a destruction of a star. But if we think classically, what do you think? You feel if you want to break something big, what do you think? You think you can break it with a thing which is bigger than that. Isn't it?
Yes.
This is how we perceive. This is how we feel is right. But really, the true story is basically small changes. This is the origin of what is known as butterfly effect. You might have heard it. Okay? And this butterfly effect was later on used in chaos theory in quantum mechanics. But it originated from this man. What was his name? Edward Lorenz. He was a materiologist. Okay? So this is how you can understand that how vast this field of perturbation is and what are its pure implications. Now, we have obtained the amplitude, okay? And if I write down the amplitude, an1 of t, okay? What is it? It is 1 by IH cross.
Yes.
Then treating my matrix element to be constant, say m, h, n, and then you have an integral. Okay, it's from 0 to t, and then you have e to the power of I, omega m n t dash dt dash. Right? You remember we had solved it, we calculated it, and what we obtained for this case was a1 of t is 4 m h n by h cross square omega m n square. What was here? Sine square omega m n t by 2. Now this is my amplitude, right? So this equation we have already obtained in our previous classes. Now we want to define the transition probability. Come on, look at the thing. Suppose you have two energy levels, energy level 1, energy level 2. A small perturbation can hit your electron in the ground state. And there is a probability that this electron will make a transition to the higher energy level. Now see, this transition will tell you the story of the atom. It will tell you what atom is. It will tell you about the spectrum that you see in the laboratory. When you check out the spectrum of these atoms. This transition that you have, this is a probabilistic transition. It's not an absolute transition. You have a probability. If you hit an electron with a photon, there is a probability. You calculate that probability using this equation. You want to calculate that probability. What is the probability that this electron will make a transition? It will make a transition to the higher energy state. Getting my point? Now, to calculate this probability, we call this Fermi golden rule. And we define this transition probability. How do we define this transition probability? We define this transition probability. Transition probability let me assume a symbol for it. Let me take it T. So what you have two energy levels. You have a photon, and say this is energy EM, and this is energy En. This photon will hit your electron. Now there is a probability that this electron can go to the higher energy level. And there is also a probability that this electron will not go to the next energy level. Are you getting my point? So the probability that it has to go to the next energy level, it's opening a window for you. It's opening the information for you about this system. It's making a big change. It's basically making a resonance. Because the electron must have its own oscillations, the photon must have its own oscillations, and you certainly mathematically feel that this electron can go to the next energy level only under certain resonance. And all other interactions in which there is no resonance, it may not find itself into the higher energy state. Are you getting it? Okay? So what we have, we define a transition probability. Say I choose a symbol T for it. Okay? Don't confuse this T with time or any other physical quantity or the kinetic energy operator. It's T. Let me choose it as a T. Okay? And how do we define this? So you have, in the real system, you have energy levels. And when you are having energy levels, you have density of states. Right? So density of states is a very mathematical indicator of giving us an understanding of the transition of an electron from one state to another state. So if I assume that rho of Em, I will choose M here, is the density of states. What is it? Density of states. Then this transition probability is defined as 1 by T integral minus infinity to infinity a n 1 of T whole square rho of E and dE of n. Right? This is how we write down the transition probability. Okay? And when we calculate this transition probability, it gives us the probability of finding an electron or your system in the next state. So this A n, yeah.
Rho E of M,
Rho Em, okay, because I have used the symbol M, yeah, it has to be En, okay? And then you have dEm. Now I can use this, I have already written down this. So I can write down the transition probability. Yeah, what will be that? So T is going to be 1 by T integral minus infinity to infinity. Okay? What is A n 1 of T? It is M H N, okay, divide by H cross square omega M and square sine square omega M and T by 2 DEM, isn't it?
4 भी है.
Okay, the 4 is, I will use that 4. Okay, here you have a 4. That's it. Okay?
Yes.
Fine? Fine. Okay, now what can I do here? I would like to, assuming that the time of your perturbation is extremely large. If the time of the perturbation is extremely large, this matrix element can be taken out of the integral. Okay? When we do that, what will be T? T will be 1 by T Okay, can I write M H N divide by H cross square omega M N square integral minus infinity to infinity. Okay, what is left? Sine square omega M N T by 2 divide by omega M N by 2 whole square. I will rather take this omega mn square here. Okay? The 2 that was here in the numerator, I have brought it down because 2 square will give us 4. Right?
Yes.
Okay? Fine. So now, here we have what? DEM. Right? Is it clear?
Yes.
Can I move on? Okay, now think about this DEM. Now, if I think of EM, it is H cross omega MN. Okay? M is the initial state and N is the final state. So EM is H cross omega MN. What about DEM? It is H cross D omega Mn. Because you see, my integral is in terms of E here. Isn't it? My integral is in terms of EM.
Yes.
But the function incorporating my integral is in terms of omega Mn. So I need to change this DEM into omega Mn. So for this DEM, what I'll use? Okay, come on. So T will be, okay, matrix M H N by H cross square. That's it. And then you have an integral minus infinity to infinity. Then what you have? You have sine square omega Mn T by 2. Then divide by omega Mn by 2 whole square times H cross D omega Mn. Am I right? Can I do this?
Square double. Yes.
Yeah, this is square. Okay. Come on, you're right. Okay, you can see this square and this H cross will cancel. Right? Will it cancel?
No. So 1 by T.
1 by T, okay, yes. 1 by T is, okay, this is T, this is the transition probability, and this is whole divide by 1 by T. Is this clear? Fine? Okay. Now what we have here? We have an integral from minus infinity to infinity of something like this, and for that we have a known integration minus infinity to infinity. If you have something like sine square x by x square dx, this is simply equal to pi. Okay? This is simply equal to pi. But in your actual integral, what you have? It is omega mn t. Are you getting my point? So when we do that, so this thing, minus infinity, you can do this manipulation yourself. You will incorporate the values. So for this sine square, omega mn t by 2 divide by omega mn by 2 whole square d omega mn. This comes out to be 2 pi t. Okay? So this is an assignment for you. You work on this integral and you can find its value equal to 2 pi t. So this part of your equation has a value 2 pi t. So I can write down the transition probability now. What will be transition probability? That is 1 by t. Then you have m h. This is hp. Okay, you correct it. And because this is the perturbation part. Okay. And then I have missed another important thing in my equations. What was that? It was the density of states. Okay? So at every step you have to incorporate rho of EM. Okay, no problem. I didn't choose to write it because it was causing problem to write down on the board, but I have incorporated it now. Okay, so this is rho E of m, and the result of that integral gives us what? 2 pi t. Now you see this t will cancel with this t. Okay, so what you will get? You will get the transition probability. Where is the h cross? Divided by h cross.
Yes.
H cross is there. Huh?
Yes, sir.
H cross is there. Check it.
Yes.
Yes, sir. Eight.
Yeah, one H cross is there. So what we are getting the final result.
2 pi by
So,
H cross.
so 2 pi by H cross integral m HP and rho of E. Now this gives you the transition probability. You can calculate the transition probability of your system using this equation, and this equation is what is called as Fermi golden rule. Is this clear? Clear?
Yes.
Okay. Now let's choose a problem, okay, and solve this problem. I think I'll give you the problem. Let me not record it now, okay? Let's stop here. Okay. I'll give you the problem. Okay, wait for a while. I'll write down the problem here because so I choose a problem in which I introduce a perturbation of V naught cos omega t. This is my perturbation. And what is my aim? My aim is to calculate the transition probability. Okay? When I say the transition probability, you automatically understand you are calculating the Fermi golden rule, right? So you have a problem, and in that problem you introduce a perturbation, and that perturbation is V naught. V naught is a constant, okay? And it has a dependence on your periodic function, cos of omega t. Omega is the angular frequency of the disturbance that you are introducing in your system. So you must have at least understood that how small changes can bring those changes which are which a common intuition will not support. A common intuition will tell you the story of wrestlers. If you have a big wrestler and a small wrestler, you will always feel the bigger one is going to win the job. But that's not the way the nature works. If you rightly remember that Apollo crash, do you remember that? In which a scientist, what was her name? Kalpana Chawla. She was from the same country, and she also died in that crash.
Yes.
And what was the reason of that crash? Was this reason classical in nature? No, the reason was never classical in nature. The reason was purely quantum mechanical in nature. And it was a small perturbation. It was a small perturbation that happened in the spaceship that led to the destruction of that massive rocket ship. And this rocket ship was carrying the most brilliant personalities of the world, including Kalpana Chawla. So this is the point here. So this is the domain that we are looking in the framework of perturbation. So come on, you stop it now, okay? So now I want you to solve this problem. I'm here with you. You try to solve it and see the results. A very good morning to all of you, and I hope everything is going fine. And today I want to extend my my class from the basic time-dependent perturbation and try to classify it into the two important frameworks in perturbation. What we have is one is called adiabatic approximation, and the other one is called certain approximation. So before we dive actually into the mathematical discussion, let me talk about something what is purely non-mathematical, what is purely not taking account of the equations of the mathematics. The point is that I want to start this class with a story of a man who basically the man who chased the shadows. And the story that I'm telling you is 2,200 years back. So, who was this man? This man was a librarian, and his name was Eratosthenes. Eratosthenes, he was a librarian, and he was the man who could mathematically, without using mathematics, because it was not the time when people had telescopes and they could see the planet from outside, or they could have the satellites roaming around the planet. This man, who was a librarian, what he did was marvelous. It was miraculous because he could focus on the observation that he observed. Now, what the title is, The Man Who Chased the Shadows. Now, what was it that this man chased? And even the advent of the time was that when you had no telescopes, when you had no satellites roaming around the planet. And what he did, what he observed is, suppose we have a well, okay, and we have the rising of the sun. And what this man did actually is he observed a deep well when the sun was exactly on the top with respect to the ground. So if the sun is exactly on the top, you will directly see the bottom of the well, because even if you will put the rods around the well, you will not be able to see any of the shadows, because that tells you that the sun is exactly on the top. And if the sun is exactly on the top, then if you fix the rods around the well, you will not be able to see the shadow at the bottom of the well. And this observation was taken by this man. And what he observed, there used to have a place in Egypt, what was called Aswan. And in Aswan, somewhat around 21st of June, 2,200 years back, this man observes the well. And what he finds that at the bottom of the well, there is no shadow. But at the same time, having another well in Alexandria. So Alexandria is towards the north of the Egypt. And at the same time, the observation was made on another well. And in that well, they could observe a shadow. So this observation is taking place. There is a record of the observation over the same duration of the time. One well is telling you that there is no shadow, the sun is exactly on the top, and another well is telling you that there is a small shift. There is a shadow at the bottom of the well. and presuming that sun is very, very big and it's very, very far away from the planet Earth, we should not obtain the shadow in the both wells if Earth was flat. So this man is coming up with an argument. He's coming up with an argument, and the argument is that if you are able to measure a shadow in a well which is in the deep north of Egypt, and there's no shadow in a well which is in Aswan, it's the same place. Okay? So the existence of the shadow on another well is an indicative of the fact that Earth is not flat. And it's this observation on which this man worked. This man, a philosopher, a librarian of that time, he worked on this problem and he came up with an argument. Even it was the time when mathematics was not developed that much. But he could calculate the shift in the angle. He could measure the distance from Aswan to Alexandria. And by doing so, he could calculate the angle. And of that time, using the geometry, the geometry that was available in that period of time, he was able to calculate the circumference of the Earth. Could calculate the circumference of the Earth to a very, very greater accuracy. So what is it that led this man to come up with a very, very huge argument? This argument is not a simple argument. It was the time when everybody believed in flat Earth. And it's this curiosity that has led this man to know the reality, to understand the nature of reality. So what am I trying to tell you is science works if you come up with the right question. And if you come up with the right question, you will certainly come up with the right answer. And that will take this civilization on and on. So this is how I feel I can impress you by telling you the stories of the past who have really worked and who have really come up with the right questions to answer the right questions. When you try to find the answer to the right questions, you certainly come up with something which is a modification to the knowledge on the planet. Now, our journey is basically, now let's stop here. Our journey is basically to move on in the framework of time-dependent perturbation theory, and our target today is adiabatic approximation and certain approximation. Maybe the second one, I don't know whether we will be able to go to the certain approximation, but we will make an argument to complete that as well. So what we have is, we have the transition probability, and we have achieved it in our previous classes. And if I write down that transition probability as t, and this transition probability is, say, 1 by I h cross, then you have an integral 0 to t, and then you have a matrix element of m, you have a perturbation, say h dash and n, and you have an exponential function e to the power of I omega m n t dash dt dash. This whole thing we have to square. So this is giving us the transition probability. Now, before moving on, I would like to make a small modification in this equation. And how can I do that? And then we will proceed in the framework of adiabatic approximation. We will define that, and then we'll go to the next approximation, what is certain approximation. So what can I do here is, if you see closely, if I write t is the same thing, 1 by I h cross, and you have the integral 0 to t, and if I introduce 1 by iota omega mn, I can do that, and I have my own matrix element M, H prime, N. And for this, I will write a time-dependent partial derivative, dou by dou t of I omega M and t dash. And then you have dt dash. And this whole thing is a square. And keep that thing in mind. Now you can see, if you take the time derivative of this exponential, it's e to the power of. If you take the time derivative of this exponential, what you will get I omega n outside. So the I omega n and n that I have introduced in the denominator, that will cancel. You will come back to your original equation. That you can understand. So this way, this iota will multiply with the iota. You will get iota square. That will give you minus. But this is the mod of whole square. That minus will go. And finally, what will be left inside is 1 by h cross omega mn. I think you can take the square of h cross. You can take the square of omega mn. So what will be your equation you will be left with? Your equation will be t is 1 by h cross square omega mn square. This is the thing that we have got out of it. Then what you have inside is the integral 0 to t, and you have the matrix element m h prime n, and then you have dou by dou t of e to the power of I omega m n t dash dt dash, and this whole square, you have the whole square of it. Okay, now this is my oversimplified transition probability of my system. Now, what I say, suppose the perturbation that you are introducing, because you are introducing the perturbation where you have a system of whose Hamiltonian can be completely calculated. And if Hamiltonian can be calculated, then what you do is you introduce the perturbation. Now what I do here is, if the perturbation that I introduce to the already known Hamiltonian, if the perturbation takes a longer time, if it takes the longer time, so what does that mean? So if I have an infinite well potential like this, and you know the potential, you know the Hamiltonian of the system, and what you do is you introduce a perturbation. But that perturbation takes a longer time. That means it goes on and off slowly. So going on and off slowly means, say for example, it started from 0 and it reached here by say 10 milliseconds, for the sake of argument. Now this kind of perturbation that you have introduced in the potential well is adiabatic. Then if this is adiabatic, then what is sudden? So for sudden, we have the same potential, we have the perturbation that we are introducing, but that perturbation lasts for say 10 nanoseconds. Now, these seem to have the same kind of perturbations, but there's a difference of time. In the first case, the time is taking longer. So this kind of perturbation is adiabatic perturbation. It is adiabatic time-dependent perturbation that you are introducing in your system. And this kind of perturbation, here you can see a shot. The same thing is happening, but it's happening in a very, very short period of time with respect to the milliseconds. Here you have nanoseconds. So this kind of perturbation is called sudden. Here we make use of sudden approximation, because things are happening suddenly. And in this case, the perturbation you are introducing to the system, it's going on slowly. So this kind of perturbation is called adiabatic perturbation. Adiabatic, here we use a mathematical approximation, what's called as adiabatic approximation. So this is my adiabatic approximation, we deal out the problems using adiabatic approximation, where the perturbation that you are introducing in your system is slow. And here, where the perturbation that you are introducing into your system is fast with respect to this, then this kind, here we make use of certain approximation. So let's go with adiabatic approximation. So for adiabatic approximation, what we have? For adiabatic approximation, we have, okay, my transition probability is 1 by h cross square omega m n square. Okay, then you have a bracket, and then you have an integral running from 0 to t, and then you have the exponential function, okay, e to the power of I omega m n t dash, okay, and then, okay, then you have dou by dou t of the matrix element m, h prime, and n, and dt dash. Okay, now this is whole scalar. This is whole scalar. That's understood. This is whole scalar. Okay, now we can see here we have an integral, and if we have an integral like this, we will use the UV form, and UV form for integration is, if you have integral of UV, then what happens? U as its integration of V minus integral differentiation of U and then the integral of V. This is how we use the UV rule in integration. So what can we do here? We can think of using the UV rule here. So what will happen here? So T will be 1 by h cross square omega m n square. That should be the case. And I think I would like to rub this because this will hinder my writings. So what would I write here is, so U as its, okay, U as its. So if I treat this as U and this as V, so what's going to happen? E to the power of I omega m n t dash as its, and then integral of this part. So when we will have the integral of this part, this differential and integral will cancel. So what you'll be left with is m h prime n. So this is your first part. What will be the next part? That will be minus integral. Differential of, you will take the differential of e to the power of I, so dou by dou t of e to the power of I omega m n t dash. Okay, so this will be the differential of, and then integral of dou by dou t of m h prime and n, dou by dou t, and the integral will go. Okay, should I do it that way? Yeah, I should. I think this is going to give me, I think I should use it other way. I mean, I will choose this as U and this as V, because that way I will have the derivative of the matrix element will exist that way. So let's do it again here. Okay, what will I do here is I will be choosing this as U. Okay, this is 1 by h cross square omega m n square. Then you have the bracket. So if this is acting as U, this is m h prime and n dou by dou t of this thing, and then you will have integral of this thing. So integral of this thing will give you e to the power I omega m n t dash divided by I omega m n. This should be the case. Okay, and then you will have minus integral, the differentiation of this. Okay, something is wrong. Okay, no, the first one was the right, I think. Come on, come on, come on. Let me rectify this because in the second case, then I will have. Uh, if I choose this, then I will have to take its derivative first. Then it will become a complex thing. So choosing the first one. So again, let's go with the same argument. I don't know. I may be wrong. Omega m n square, and then you have this thing as x, so e to the power of I omega m n t dash as x into the integration of this will lead us to the matrix of m, h prime and n, then minus integral 0 to t, okay, then you have the differential of the first. The differential of the first will give me e to the power of I omega m n t dash by I omega m n. That's fine. Okay, that's right. Yeah, I think what we were doing previously is taking us to the right direction. Okay, so here you will have the integral of this thing. So differential and the integral is going to it's going to cancel. So what you'll be left with is m h prime n. Okay, that should be the case, and then certainly you will have dt dash, and that's fine. Yeah, this is the correct result. Okay, so this is the correct equation, and this certainly will take us to our destination, because what we have been discussing is the adiabatic approximation, and what we are assuming here is that the time of evolution, the time of operation via perturbation is very, very large. So you can see here this part of the integral where you have 0 to t, this part of the integral is going to vanish, and you can understand that in terms of, because the perturbation that we assume here, we are introducing a potential V0 as the perturbation, and this V0 will be 0 at t is equal to 0, and this V0 will be 0 at t is equal to whatever is the length at t is equal to t. So using this boundary condition to this equation will lead us that this part of this integral is equal to 0. So if this part is equal to 0, so we are left with this part, t is equal to. So t is equal to, so the transition probability is 1 by h cross square omega mn square. And then what you have an integral now from 0 to t, and inside the integral what I have e to the power of I omega mn t dash divided by I omega mn, and you have the matrix element m h n and dt dash. Alright, so this t, since we have a problem of adiabatic, so what we can do, this matrix element is going to evolve very, very slowly, so this will behave as a constant. So t will be 1 by h cross square omega mn square, okay, and inside what you will have, okay, what will be outside is m, h, and h prime and n. This will be whole square, because this thing is all square, okay? And you will have this integral part, e to the power of I omega m n t dash by iota omega m n dt dash 0 to t. And this thing will take us to, we have already done this part, this thing will take us to sine square omega n by 2. So what you will have t equals 1 by h cross square omega n square, and then you will have n h prime and then you will have sine square omega n t by 2. We check it again. I feel maybe something wrong has happened, but let's check it. Okay, so you have exponential as its, and you will have the integration of this part. So that will take this out, so you'll be left with this. And then you will have integral, the differential of the first part. The differential of the first part will lead us to this. And then the integral of the second part will lead us to this. Okay? And it seems to be correct till now. So this part is going to vanish in the framework of boundary conditions. And this part is going to exist. And what you'll be left with, because you are treating your system adiabatically, you are getting this part, the scale of this part is getting out, and you're left with this part. This part is already calculated, and it results into sine square omega n t. Now, this part that we have, so it has to be the square of this, I'm sorry. So 1 by h cross square omega n square n h prime n square. This will be very, very less than, if I define the two levels, say E1 and E2. This will be very, very less than E1 minus E2. Now, if this part is very, very less than the energy difference between the two levels, that means this part will tend to 0. And this part will automatically tend to 0. And what does that tell us physically? That tells us that if your system is subjected to something what's called adiabatic as I explained it, slowly. In this case, the transition probability, because you're calculating the transition probability, this transition probability will tend to 0. That means there is no chance for an electron to make a transition from ground state to the excited state. So adiabatic approximation leads us to a conclusion that there is no transition. There is no transition of electron from the ground state to the next energy state. So this is how adiabatic approximation is treated, and this is how it tells us, it gives us an information of no transition probability for your system, and which is certainly consistent with the photoelectric effect. If you rightly remember the photoelectric effect, ejection of an electron, it's a very spontaneous process. So for something like photoelectric effect, you won't expect an adiabatic kind of thing, you will expect a certain kind of thing. And certainly there has to have that probability involved in that certain approximation. So I think here I would like to stop it, and I would like to move on with the next approximation, what is called as certain approximation. Now, in case of certain approximation, what do we expect? I have checked that. So I would like to stop here, and let me go back and come up with certain approximation. Now this is our transition probability. This expression is already evaluated, and let's proceed from here to reach out to a simplified equation, and then from the result that we will obtain from solving this and modifying this equation, uh, there we would like to discuss the two important approximations. One is adiabatic approximation, and another one is certain approximation. I have already given you the explanation what adiabatic means and what certain approximation means. So the perturbation that you are introducing in your system, if it goes for the longer time, if it evolves over a long period of time, then the perturbation that you are introducing in your system is adiabatic in nature, and you make use of adiabatic approximation. And at the same time, if the time of the perturbation that is introduced in the originally known system, this kind of approximation is what's called as certain approximation. So let's formulate this equation a little bit. So what we can do is we can think of writing this t as 1 by I h cross integral 0 to t, and you will have matrix element h prime, and here I will introduce the time derivative dou by dou t, and this is e to the power of I omega m n t dash dt dash. But since if you take the time derivative of this exponential function, you will have something in the numerator. What will be that? Will be the internal derivative of this exponent. So here if I write I omega mn, so what's going to happen here is once you take the time derivative, I at omega mn will come out and they will cancel. So your equation is not going to change. You will retain the originality of your equation. So this is whole scalar. So what we can do here is we can multiply this iota scalar. It will give us -1. Since you have a whole scalar, so it will automatically become plus. So what will be outside will be 1 by h cross scalar omega mn scalar. Then inside you'll be left with the integral 0 to t, and you have the matrix element m h prime n e to the power of, no, it has to be the time derivative of dou by dou t of e to the power of I omega m n t dash dt dash whole scalar. Now, proceeding from here, what we would like to do is to integrate this these things which are within our integral limiting from 0 to t, and then obviously we are supposed to take the scalar of that. So what we'll be left with is we will have the transition probability. It will be 1 by h cross scalar omega mn scalar. Okay, you can think of using the UV rule here, and if you use the UV rule, what will happen, treating the first matrix element as u, so it will be m, h prime, and n, and integrating the exponential part will give you e to the power of I omega n t dash, because the other part is the time derivative of the exponential. Once you integrated, this differential and integral will cancel, so you'll be left with e to the power of I omega mn t dash. Then you will have minus integral 0 to t, and the differential of u, that's dou by dou t of m h prime n, and the integral of this part, again, this differential and integral will cancel, so you'll be left with the exponential function. So you will have e to the power of I omega mn t dash, and you will be left with dt dash. Now at the same time, this is the whole square. We have to keep in mind it's all square because we are calculating the transition probability. We're boiling down this equation to some reference equation where we can discuss the result in terms of the adiabatic approximation, and then we can take this discussion to the certain approximation. So what's going to happen here is looking onto the boundary conditions of our problem at t equal to 0, the perturbation, which is h prime, and in our case assuming it to be v naught, this v naught will be 0, and at t equal to t, again this perturbation, that is h prime, v naught, this will vanish. So what's going to happen in the first part of this bracketed term? This bracketed term will automatically lead to 0 when you apply the limits to this result from 0 to t. So this part of the bracket will cancel. So your transition probability will come up as, so t will come up as 1 by h cross square omega m n square, and then you will have the square of that integral, so the minus will automatically go. So this will be integral 0 to t dou by dou t of the matrix element m, h prime, and n, and then, and then you will have the exponential part e to the power of I omega m n t dash dt dash. But this is all square of it. So this is all square of it, and this is my basic equation, and I would like to use this equation to discuss the two important cases. The first case is adiabatic approximation. Adiabatic approximation. So in adiabatic approximation, the assumption is what? The assumption is that the perturbation that you have introduced, it's going to vary slowly in time. So if the perturbation that you have introduced in your system is varying slowly, then this term, the time derivative of this matrix element will be treated as a constant. So it will come out of the integral. So in that case, t will be 1 by h cross square omega m n square, and dou by dou t of the matrix element m, h, and n. H prime is the perturbation, and then you'll be left with 0 to t e to the power of I omega m n t dash dt dash. Now what is important is that this is whole within the brackets, and you have to take the square of it. Now if you take the square of it here, you will keep the square for this whole thing, and you would like to keep the square for this whole thing. And you can see from our previous classes, we have already integrated this kind of function, the exponential function, that's carrying the same symbols as the symbols that you can see here. And the result of this integral is, it is sine square omega n ln by t. So what will be t here? So t, the transition probability, is going to be 1 by h cross square omega m n square, and then you will have dou by dou t of the matrix element of m, h prime, and n, and this whole square. And the result of that integral will give us sine square omega m n t by 2. Now what does this equation tell us? This equation tells us, suppose you have two energy states, say this is E1 and E2, assuming that E2 is greater than E1. Now how we can translate this equation into an adiabatic approximation, one is that this term that you have, what is this? This is 1 by h cross square omega m n square, and dou by dou t of n h prime, and the square of this this whole value is very, very less than the difference in the energy, say E2 minus E1. Or let me call it E1 minus E2, because the transition has to take place from E1 minus E2. Now, since the term that's here is very, very small than E1 minus E2, then you can simply say that this term is tending to 0. And the transition between E1 minus E2, it's also tending to 0. So what does it mean? It means when your system is evolved adiabatically, then the probability of the particle, say for example an electron in the lower energy state, the probability for this electron to move from the ground energy state to the first excited state is equal to 0. There is no transition probability. You will not make any transition. Your system will maintain its originality even though you are introducing the perturbation to your system. Now the next case is the certain one. So in case of certain approximation, so what's our basic equation is T is 1 by h cross square omega m n square, and you have a bracketed term. Then you have an integral from 0 to t, and you have the time derivative of the matrix element, and you have the exponential function e to the power of I omega m n t dash dt dash. This is all bracketed to a square. Now, in case of certain approximation, as I explained to you in the beginning of this class, that for certain approximation, the perturbation that you are introducing in your system, it takes a very, very short time to evolve with your system. So if it takes a very, very small time to evolve with your system, in that case, this exponential that you have, this exponential will act as a constant. So for certain approximation, the exponential part of this equation will come out of the integral. So what will come t as? So t can be written as 1 by h cross square omega mn square, and then you will have e to the power of I omega mn t dash by nothing raised square, and what will be left inside in the integral is 0 to t dou by dou t of m h prime, which is the perturbation that you are introducing, and this perturbation is there for a very short span of time. This will be whole square. Now you have an exponential function. You have to calculate its magnitude. So when you calculate its magnitude, it's a complex function times its complex conjugate. It will lead us to the number 1, because when you multiply the two, you will get the power is power 0, and anything raised to power 0 will take us to 1. So transition probability will come out to be 1 by h cross square omega mn square, and then you have your own 0 to t. I think you can also cancel this integral with the derivative. So when you do that, what you'll be left with is m h prime n whole square. Now what does this equation tell us? This equation tells us that you have a probability of transition, that your particle, your electron, will make a transition from the ground state to the first excited state, say in the case of an atom. So your system will accurately make a transition. There's a very good probability of making a transition, and that transition has to be allowed transition. The transition will take place from one energy state to another energy state, because your transition probability is simply depending on the scale of the matrix element. So what is the conclusion of the two results that we have obtained? The first one was adiabatic approximation. In adiabatic approximation, we assumed that the time evolution is very slow. The system is adiabatically evolving. The perturbation that you are introducing in your system is adiabatically evolving. In that case, we saw that the transition probability is zero. There will not at all any kind of transition take place from one state to another state. But if at the same time, if we decrease the evolution of time, if we decrease it marginally to a very, very small shot, then there is a measurable probability that the electron may make a transition from one energy state to another energy state. So with this, I hope you find this useful. I hope you find this helpful to proceed on to solve the problems based on these approximations.